This is Jantar Mantar in Delhi. It's one of the hot spots for tourists coming to the city. But that is not the only reason why this place is famous. An important concept in physics is demonstrated right here by the structure Jantar Mantar. And here's a hint, it is very relevant to today's episode on measurement and error analysis. What is the connection? And what is this place all about? We'll find out more about it in today's episode. Hello and welcome to the show. Our episode today is on measurement and error analysis. If I asked you to give me the exact number of people in a room, you can possibly give me the correct number. But if I were to ask you how many atoms are there in a room, giving an exact answer is almost impossible. It doesn't mean that you have erred in your measurement. Error in a scientific measurement doesn't always mean blunder. It instead can refer to unavoidable imprecision in measurements. So let's learn more about it today. In this episode, our objective would be to get introduced to SI system of measurements, identify the sources and types of errors, and of course, the segment you all look forward to, the exam decoded section. The word measurement comes from the Greek word metron, meaning limited proportion. And metron in turn shares its genealogy with moon and month. You see, the moon and various astronomical objects were then the measurement methods of time. And look how far we have come. Physicists recently calculated that we have 1 extra second in 2005. They called it the leap seconds. Anyway, in ancient India, the duties of the king included the examination of weights and balances every 6 months to ensure correct measurements that were marked by the royal stamp. Even in engineering, as far back as 5,000 years in the Harappan era, standardized sizes of bricks were found in buildings of the entire region. But all that is in the past. The modern world needed a standard of measurements compatible with one another. Shopping for your groceries? It's a familiar situation for most of us. While you make sure that the brand that you pick up is right and it's the right quantity, you never really stop to wonder if the measurement stated on the back is actually accurate, do you? Of course, you don't have to worry about it, because it turns out that measurements of physical quantities such as mass, weight, and volume have been standardized in such a way that a kilogram is a kilogram no matter where you are. Each country has a National Meteorological Institute to maintain a standard of measurements. In India, it is the National Physical Lab that makes sure our lines and lengths don't fall short. Let me now take you for a tour of the National Physical Laboratory in New Delhi, India's premier research lab, which is also the custodian of measurement standards in India. Phew, heavy job. Research, testing, calibrating, NPL does it all. Being at the forefront of standards of measurement and the apex body for calibration is quite a challenge, isn't it? Since physics is an experimental science, experiments require measurements, and we use numbers to describe these measurements. But numbers are meaningless without ascribed units. The system of units used by scientists and engineers around the world is commonly called International System of Units, or simply the SI system. Moving on, there are two types of units as per SI system: fundamental or base units and the derived units. For example, in SI system, length and time are measured in base units of meter and second respectively. The derived quantity speed is distance travelled divided by time. So it is measured using derived unit of meter per second. The table here shows 7 base units as per SI system, that is meter, kilogram, second, ampere, Kelvin, mole and candela. With these base physical quantities and units in the repository, we can attempt to carry out any measurement. Even measurement of very large distances like the distance between Earth and Moon. Let's see how we'll do it. We use a method called the parallax method. To understand what parallax means, just try this activity. Draw a dot on the wall, shut one of your eyes and hold a pencil in your hand at arm's length and look at the pencil through the other eye so that it covers the dot on the wall. Now close the eye you are using and open the other eye. The pencil's position will seem to have shifted because you'll notice that you can see the dot on the wall. This apparent shift in the pencil's position against the dot in the background is called parallax. The parallax is more apparent if you focus on an object very far away. For example, try to cover an antenna on a rooftop with a pencil. But why is parallax caused? Parallax is caused whenever there is a change in the point of observation of an object. But how can this method of parallax be employed to measure as great a distance as the distance between Moon and Earth? Well, the Moon is observed from two diametrically opposite points A and B on Earth. The angle theta subtended at the Moon by the two edges is 1 degree 54 minutes. Here, the distance B between the 2 points of observation corresponds to the diameter of the Earth, and D is the distance of Moon from Earth. If B is a lot smaller than D, and therefore theta is very small, we can approximately take B as the arc length of a circle with radius d. Then arc length B is equal to radius d times theta. Knowing theta and B in this equation, d, the distance between Earth and Moon, can be found. Using very simple measurements, we can estimate the size of a molecule. Yes, I really said that. But that is theoretical. Physics is real. So let me show you how to easily measure the approximate diameter of a molecule. What we need is to form a thin film of oleic acid molecules on the surface of water. This needs to be the thinnest possible film in a small container. But before you pour the oleic acid on water, use this graduated beaker with volume readings to measure the volume of the pure oleic acid dropped on the surface of water. Then measure the area covered by the oleic acid, which is just pi times the radius of the beaker square. Now it is possible to calculate the thickness of the monolayer using the equation volume is equal to area A times the thickness T. Knowing the volume and the area of spread of the acid on water, thickness T can be estimated. Here, the volume of the film corresponds to the volume of dilute oleic acid that I poured on the water. Note that the shape of the oleic acid changes when it's poured from this beaker onto the water, but the volume, which is the amount of space taken by it, will not change. Also note that the thickness T will correspond to the diameter of the molecule if the layer is the thinnest possible. And now it's time to see how attentive you have all been. So here is a little quiz for you. Which clock maintains the Indian Standard Time? A cesium atomic clock at National Physical Lab in New Delhi, Clock Tower Shimla, or clock at Jantar Mantar, New Delhi? Well, for more such questions, don't forget to visit our website topperlearning.com. Think about it because we just went over it a little while ago. Now I'll take a short break, and when we come back, we'll solve more problems. Stay tuned.